Today I will be quickly reviewing the different types of functional groups for organic compounds and also identifying the priority of them. I will be listing a few polar properties of some of the functional groups, and I will have an assortment of sample problems at the end for you to try. Okay, so we have alkanes, which only contain single bonds, alkenes, which one or more double bonds, alkynes with one or more triple bonds, and halides. Alkanes are not actually a functional group, they lack a functional group, but they're important for organic chemistry. So we have alcohols, we have ethers, aldehydes, and ketones here. I put this structure on the side so you could see. Aldehydes and ketones are different because aldehydes are always on the end and ketones are always in the middle of the chain. We have carboxylic acids and we have esters. Carboxylic acids have the double bonded oxygen and then they have a hydroxy group attached. So the suffixes for these alcohols, it ends in "-al". For ethers, it's special, or it's a little bit different than the others. I'll show you an example further on. We have aldehydes, which is "-al", ketones, which is "-one", carboxylic acids, which is "-oic acids", and then esters end with "-o-ate". There's also the amino functional groups. So first we have our primary amine, which, as you can see, it has it has both hydrogens attached to the nitrogen and then it has another chain. Then we also have the secondary amine that has two different chains attached and the hydrogen attached to the nitrogen. Then finally you have the tetrary amine, which has three different chains attached to it. The suffix for all of them are amine. So we also have aromatic hydrocarbons. The first one here is a benzyl, and this one's a phenyl just below, and the phenyl just contains the ring and the extra carbon chain. The benzyl, it's separated by the methyl group and then the rest of the chain. So moving on to the rules for naming hydrocarbons with multiple functional groups, first you want to find the longest carbon chain. The second step is to identify the highest priority functional group. I'll show you what they are in the next slide. And then you want to number the hydrocarbon chain to give that priority group the lowest number. And finally, you want to identify any other substituents and their position on the hydrocarbon chain. Moving on, it's important, very important, to be able to identify the functional groups based on their priority so that you are able to list and name the unique and unambiguous structure. Here are the priority groups. So carboxylic acids always have the highest priority in the molecule. So then it's followed by esters, amides, aldehydes, ketones, alcohols, then you have amines, and then it's alkynes, alkenes, and alkanes, followed by ethers, and then alkyl halides. And alkanes, ethers, and alkyl halides all have the same priority, so when you're naming them all in the same hydrocarbon, you just want to have the smallest total for your numbering. So here's amides. I didn't mention them before, but here's the structure. So you have the double bonded oxygen to the nitrogen group, and then you also have the rest of the carbon chain. It's different from amines in the double bonded oxygen. To expand on the topic of functional groups, I just wanted to talk about polarity but not go too in depth. So the greater the polarity of the molecule, the higher the priority. And just to specify, this is only with the functional group, not considering the rest of the molecule. So here we have alkanes, alkenes, and alkynes, and as you can see in the alkanes, there's no hydrogen bonding present. There are no electronegative atoms there, and then it's a nonpolar molecule. Alkenes are similar to the alkanes, but they do have the double bond there, which makes them more polar as a result of their orbitals, in specific their p orbital being larger. Alkynes are similar to alkanes and alkenes, however, they are even more polar because, again, they have a triple bond which has two pi bonds, and therefore their orbitals, in specific, again, their p orbital is larger, which increases their polarity. Next is the aromatic functional group. So this has 3 double bonds, which means it has 3 pi bonds, and therefore it's more polar than the alkene, or the alkenes and the alkynes in the p orbital. It's larger. So next we have some more. We have ethers, halides, aldehydes, ketones, esters, amines, alcohols, and carboxylic acids. I paired them together based on similarities between their polar properties. So ethers and halides, their polar atom is added to the molecule, or an electronegative atom, oxygen, so this increases the polarity. Aldehydes, ketones, and esters, they have a larger dipole moment because of the added carbonyl group, which is composed of the carbon atom double bonded to the oxygen, which is more electronegative. Also, the double bond increases the polarity compared to the above molecules. Again, the p orbital is larger, which increases the polarity. So next we have amines and alcohols, and in these functional groups there's hydrogen bonding present, which makes the molecule more polar because of the added electronegative atom. And the thing is, alcohol is slightly more polar than the amine because oxygen is more electronegative than nitrogen. Carboxylic acids are the most polar out of all these functional groups here. They have extensive hydrogen bonding, and the molecule itself has more electronegative atoms than the previous ones. It has 2. It has the double bonded oxygen, and it also has the single bonded oxygen. There's also a greater dipole moment in the carboxylic acid compared to the other molecules. So next there will be some examples. For this one, I want you to pause the video and try and find the functional groups yourself. Okay, so you would have paused the video. First, here is a ether. So you see the oxygen separates one group from the other. Next, we have an alcohol up here, but the thing is, it is directly attached to this aromatic group, which is a phenol. So this alcohol would be present in the formula by phenol. So that would be how it would be labeled. Next, you would label the amide, which you can see with the double bonded oxygen, and then there's the alkene with the double bond. So this compound is actually capsaicin, so it's an ingredient used in arthritis pain relief. So next, please pause the video and try to name these yourself using the rules. Okay, so you've paused the video, and now I usually label all the functional groups and then I determine the priority. So here we can see the ketone group would take priority over this hydroxy group. I said hydroxy instead of alcohol because it's not the priority. And then you go 1 to 7 all the way down, starting close to the ketone. So then you'd also label the methyl group as a substituent. And I usually label or keep track of what number. So there's on carbon number 5, you have the hydroxy group. On carbon number 6, you have the methyl. And then it's a 7 carbon chain, so it's a pentane 2-one because of the ketone there. When you're naming it, it's important to keep in mind alphabetical order. Hopefully you've paused the video again to try the second compound. So here I label again all of the functional groups that are present, and then I can pick which one takes priority. So here you have the carboxylic acid on the end, which you would start by labeling given it the lowest number, so it would be on carbon 1. You'd also want to figure out how long the carbon chain is, so it's a 5 carbon long chain, so it would be pent. So then you also have the carboxylic acid at carbon 1. I find it useful to mark down where each functional group is just to keep track and make it easier for when you're naming it. You have the hydroxy group on carbon number 3, you have the chloro group on carbon number 4, and then you have an ether. So this is a special case I wanted to show you guys. So here, in this case, you want to give the oxy, put the oxy at the end of the chain on either side of the oxygen that is the shortest. So in this case, it would be meth, or methyl group. So it would be methoxy, and then you'd put the rest of the name later. But that's how you would label an ether. So here again, when you're going to label it, you want to look at the carboxylic acid at carbon 1 that takes priority. That'll be the final the final part of the name. So you have 4-chloro, keeping in mind alphabetical order. Then you have 3-hydroxy. Then here you have the 5-methoxy because it's attached to carbon 5. And then finally you would add pentanoic acid at the very end.